All right, hello class, and welcome to lecture 4. In the previous lectures, 1 through 3, we've gotten to the point where we can take physical invariants of the system, so say energy and angular momentum, and we can use those to calculate the orbital invariants, the geometric invariants, A and E, right? And now we're going to concern ourselves with motion as a function of time. Now this problem was partially solved, right, when we got the polar equation, R of t equals p over 1 plus e cosine f, right? Also a function of t. Right. In that, we could add to this, based on this little analysis here, we could convert back and forth between r and v, of course, and the true anomaly, our third orbital element. Right. So given f, we can find r, and given r, we can invert this to find f. Right. So we can go back and forth between r and f. Right, just we showed how to invert the polar equation in the previous lecture. At this point, however, we are confronted with the problem of propagating the orbit forward in time. That is, predicting when the orbit will reach a particular position, or figuring out what position the orbit will be at a particular moment in time. Or conversely, given a position, when will the orbit be there? So this question, right, what we're really looking for is a conversion back and forth between r and, of course, v, because once you know r, you can use the vis-viva equation to find v. Right. So r gives you v through the vis-viva equation. Right, so the question now becomes, how do we convert back and forth from r to t? Now, obviously, we have r in front in terms of f, and so really the question is asking, we'll just put a little break in there, can we convert back and forth between f and t? Right, because r and v are synonymous with f. So that's the question we pose in this lecture. And this is a very important question. In fact, you could argue that for all of Newton's equations, force F equals ma and universal gravitation, it didn't really do much except for verify Kepler's 3 laws. With the exception, and of course Newton saw that this was important, and this is where the Newton's algorithm comes from, Newton iteration. Except for the fact that now, armed with these equations, in particular the polar equation and Kepler's equation, which we'll cover in this lecture, we are able to predict now the position as a future point in time. And so this gets around or obviates the need for Kepler to slowly integrate these triangles as a function of time, right, adding little bits of area, until he figures out where the true anomaly will be as a function of area. Because remember, Kepler did give us area swept out as a function of time, right? He gave us an expression for a dot, which is, here's the center of the ellipse, right? A dot, A is that area swept out by the body. Right, so we have an expression for a dot, that was just h over 2. And so the area swept out, we have an expression for that. That's h over 2 times delta t, or actually I should say delta a. But the question, of course, is how to relate this f to delta t, right? Delta f to delta t. Now, obviously, we're not going to go straight. We're going to work through area because we know how to predict area. But the conversion is not necessarily very straightforward. In fact, there's no analytic expression for it. It's a transcendental equation, and there's no analytic solution that we're aware of. So That's the goal of this lecture then, to be able to convert between area and true anomaly so that you can then, right, convert from T to A and get F, right? So we'll get rid of the middleman here. We're going to go from T to A and then A to F. And so it's going to be a sort of a two-step process there. So that's the goal of the lecture. And in part A, we'll derive the necessary equations to set this problem up. And we'll see that one direction is actually a little bit easier than the other. In fact, going from F to T is a little bit easier than going from T to F, as we'll see. But in the end, we'll get both directions. So just a basic introduction, right? The problem is we've used A, H, and E to find our geometric invariants, A and E, or P if you prefer. And now our goal is to be able to propagate forward in time. So this is given a R of T naught. We'd like to be able to predict R of T, say P, in some time in the future. So in particular, this equation poses a question of 4 hours in the future. Where will our satellite be 4 hours in the future? Right. To do this, however, requires, as I said, several steps. And in particular, right, this conversion between T and F passes through various intermediate quantities. In particular, we'll introduce the concept of mean anomaly. So T, we go from T to mean anomaly. And then from mean anomaly, we'll go to actually eccentric anomaly. Which I haven't defined yet, and that conversion is a little bit trickier. And from eccentric anomaly, then back finally to true anomaly. So that's this step is the Kepler equation, right, which is this bit right here. Right. So of course, going the other direction, actually, you don't need the Kepler equation, but that's the outline of what we're going to process today. This part of it, easy, not particularly difficult, right? This part. This part and this part, well, actually this part, actually I should say, sorry, the Kepler equation applies to this part right here. Going from mean anomaly to eccentric anomaly and back and forth. And then this one we have actually an analytic formulation for expressing the eccentric anomaly in terms of the true anomaly and vice versa. So anyway, most of these results are based on simple, what do you call it, geometry, trigonometry. And in fact, we'll be using a lot of very basic mathematics here, trigonometric relationships and so forth. And so the technology here is not terribly complicated. There's no huge cross products or dot products or anything like we saw in the lectures 2 and 3. But still, there's enough of it to warrant us spending a considerable amount of time on it. Right. So let's get started. As I sort of stated on the introductory slide, we have a way of converting from R back and forth to F, right? Or back and forth to F through the polar equation. And this works for elliptic, parabolic, and hyperbolic motion. Once you have true anomaly, however, propagating that true anomaly forward in time is much more difficult, right? So finding an expression for F, a map between T and F of T, is much more problematic. Now, I should say, and I haven't said this so far, so I should go ahead and make my caveat, that this entire lecture 3, applies only to elliptic orbits. Anything beyond the polar equation, so this conversion still works for hyperbolic orbits. But after that, the conversion to mean anomaly, and in fact the conversion from mean anomaly to eccentric anomaly, and eccentric anomaly to true anomaly, none of those equations are going to hold for the hyperbolic case. And in fact, that's the question we pose in lecture 5, actually reproducing these steps. Lecture 5 is a little bit shorter than this one. Reproducing these steps for hyperbolic orbits. We don't use the universal variables formulation, which actually Pressing and Conway, our textbook, does, simply because I don't feel that it gives quite the same level of intuition that dealing with these cases separately produces, because they're, really they're based on separate analyses. We'll talk about the development of the hyperbolic anomaly and Koches and cinches and stuff when we talk about hyperbola. In any case, so having said this, I should say elliptic orbits only. And that applies to this entire lecture. Right. So anyway, how are we going to find a function f as a function of t? Well, we don't. It's not uniform, right? The f is not a linear function of t. So there's no easy clock for this problem, but we do have a clock, which we can calculate, which is Kepler's second law, which is equal areas and equal time. So we have an expression for a dot, as I mentioned earlier, which is just h/2 as a constant. And so we can find, of course, a as a function of time, area swept out. And by area, of course, I mean, if we look at this circle here, right, this is the orbit. Pay no attention to the inscribed circle. This is the orbit here, right? And this is the area swept out. So this is A. We're going to denote it Fvp, right? For these are the vertices of that area that's been swept out, right? So we have an expression for Afvp, right, as a function of time, which is just, you can express it as h/2 times delta t, right? Or you can also express it, which is actually the process we're going to take, as the area of the ellipse, pi ab, times delta t over period. Anyway, so we'll come back to that expression later. But what we don't have, of course, is an expression for true anomaly as a function of area, right? So if we had an expression for f as a function of area, right, then we could just substitute this into that formula and we would be able to find the true anomaly. But we don't. We don't have that expression. And so we're going to have to take several intermediate steps in order to find an implicit expression for that f of a as a function. Okay, let's start going through that. So our first step is to actually move away from the polar equation somewhat. So the polar equation, remember, describes an ellipse in polar coordinates. Unfortunately, finding areas in polar coordinates is somewhat more complicated. So if we look at our little area that we're most concerned with, this one right here, color within the lines. Tell my daughters that. Right. So if we look at this expression, this area that we're interested in, well, this is actually quite complicated, right? It's not obvious that there's a way to express this area in polar coordinates and in some kind of easy manner. However, if we move to rectilinear representations of the ellipse, then things get a little bit easier because we at least know how to calculate triangles, right? We know how to calculate triangles. The only thing we know how to calculate in polar coordinates is basically sections of a circle. So actually, if we were interested in it, we could calculate the section of the circle, but that doesn't really require polar coordinates, right? We could that section of the circle is just here using this e. That's pi r squared. Actually, it's just 2 pi e. Actually, technically, 2, I believe. Right. So we can calculate some things, and not many things in polar coordinates. So we're going to shift the analysis here over to Cartesian coordinates. And so to do that, we write down what is the Cartesian representation of an ellipse, right? So the Cartesian representation of an ellipse is, if you may remember, x squared over a squared plus y squared over b squared equals 1. Right? So, of course, in this case, right, this is an ellipse, not a hyperbola, so don't get that confused. And so, armed with this, actually, what we're going to do is find some of these lengths. So this is, right, this is the The green part, which used to be blue, so now it's green, is the part we're interested in. And so it's important to us to be able to determine as many of these lengths here as possible. And so in particular, we're interested in this point particularly. And so we would like to be able to calculate, say, this length PS, for example, or OS, or SF, and so various things like that. And so the first thing we're going to do is we're going to represent the vertical component of this point as a function of the horizontal component. So in particular, if we call the coordinates of this point YE, XE, oops, right, then we can find a parameterization of this point, right, YE as a function of XE just by solving this Cartesian representation of the ellipse. So I'll just write down E here, just for no good reason. I'm a little hesitant to do that, of course, because I'm actually also interested in the position of this point. Right? So why am I interested in the position of that point? Well, I better introduce the concept now of this inscribing circle. So obviously, circles are a little bit easier to deal with than ellipses. We have more known quantities about them. And so a useful geometric tool is to take the ellipse that we're analyzing, right, which here I'll just highlight it in some color here. So that's the ellipse. And inscribe it in a circle centered at the same point. So the center is the same. The radius of the circle is the semi-major axis. So A becomes the radius of the circle. Inscribing circle, that is. And so the circle meets the ellipse at 2 points, each end of the major axis. So they intersect here and here, but nowhere else. We use this because we're going to use it on the next slide to define what we call the eccentric anomaly, which is it's a bit eccentric. So I'll talk about it on the next slide. In any case, an important point, as well as this point, an important point on this inscribing circle is the point directly above in Cartesian coordinates, our position vector, right? Because remember, this is our position vector, right there. And that point we're going to say is, say, YC comma XE if you want. So YC as a function of XE, right? It's the same. The formula for the circle is the same. It's just slightly modified, where we take B equals A, x squared plus y squared equals a squared, right? That's just the formula for a circle, right? X squared plus y squared square root equals a. Right? So again, we can solve this for y equals the square root of a squared minus x squared, c in this case. And so we have an expression for, right, the point directly above our point on the ellipse. And so if we then write down the ratio of that number, right, yc over ye, right, we just plug in both of these formulas, and the a squared minus x squareds cancel, and so we get just b over a squared minus x squared over square root of a squared minus x squared, and these two terms cancel, and so the sorry, I have these upside down. And so if you want to find the point on the ellipse and you're given the point of the circle, you just multiply by the factor b over a, and that gives you the point on the ellipse. So this has a name. It's called the Ellipse Scaling Law, and it's a way to go from the circle to the ellipse. It'll be useful for calculating volumes and lengths and so forth. Okay. All right, so let's go on to the next step. So now, armed with this inscribing circle, right, which I think I was making orange on the previous slide, right, meeting up here at the end of the major axis. This is the center of the ellipse, and the center of the circle. This is the focus. Right. So the eccentric anomaly is, well, remember we've got a true anomaly, which is this angle right here. The eccentric anomaly is a artificial angle. It's something that's not something you can actually measure because, right, this auxiliary inscribing circle is not actually a thing. You can't actually observe it, right? It's an artificial construct and it's a mathematical construct. So it has no physical meaning per se. Well, it has a physical meaning. I guess you could create such a thing. But anyway, it's just a tool. So let's not get carried away. And what is it? What is this tool? Well, this is a tool which is intermediate. We're going to use it as an intermediate value between t, a, and there's e there. And then we'll use it to get f. Fortunately, the conversion between e and f is actually not that hard, although we have to spend a slide or so on it at the sort of towards the end. But the step from E to A to E gets a little bit easier if you use the eccentric anomaly. So what is the eccentric anomaly? I've talked about it enough. I should actually define what it is. It's opposed to just the motivation. So the eccentric anomaly is what is the angle you measure if you take your point on the ellipse, that's right, r of t, and you drop a vertical, perpendicular, straight down to the major axis, and then you go straight up, right? So up to the inscribing circle, right? So on the previous slide, this was, I think, P, and this was Q. Right? So if you go straight up from your point here, remember this is F, V, and P, right? If you go straight up from P to the inscribing circle, and then draw the line from the center of the circle to that point, that angle here is the eccentric anomaly. Right? So it's obviously not the same as true anomaly, right? This is true anomaly, right? This is eccentric anomaly. So obviously not the same as eccentric anomaly, and it can vary significantly between. There can be significant variations. Here they're sort of both pointing the same way, but I could easily draw the case where, say, f is here and then eccentric anomaly is here. So this could be acute while this is obtuse. Right? So that's another thing to keep in mind. There can be significant difference between the two. Of course, if the orbit is circular, they're exactly the same thing, and we don't need to fuss with this stuff at all. But of course, the whole point is that most orbits are not circular, so we have to deal with that case. Right, and of course, none of the eccentric anomaly you can see, right, just by what is called eccentric anomaly, doesn't. Well, actually, you can't really suddenly, but it doesn't apply to the hyperbola. In fact, when we get to lecture 5, we'll define something equivalent called the hyperbolic anomaly, but we're not there yet. Right. So that's what the eccentric anomaly is. And we use it, of course, because it's a little bit easier to calculate these areas as a function of eccentric anomaly, as opposed to true anomaly. So remember what we're looking for. We're looking for Afvp, which is, again, right, this, I get carried away coloring things here. My favorite thing to do is very, very satisfying. Right, sorry. So we can calculate Afvp as a function of time, and we would like to use that to calculate the eccentric anomaly as a function of time. That's a little bit harder, actually. So actually what we're going to be doing is we're going to be calculating, what we would really like is a function of eccentric anomaly as a function of this is Vp, Fvp, which we then know as a function of time. But of course, that's harder problems. So actually what we're going to be doing is calculating Afvp as a function of eccentric anomaly, and then trying to invert that expression. So that's what we're looking for, Afvp as a function of eccentric anomaly. Now, okay, what's the step here? Why are we interested in that? Of course, because we can find the Afvp as a function of time, right? Afvp is just, as I said on the previous slide, the pi AB divided by the period times delta t. Or, right, if we prefer, we can move this over here, and actually we will because it gives us a slightly easier expression. We'll drop the pi AB down here to get areas on both sides because things then cancel out a little bit better. And so we get AFvp is a function of the fraction of AFvp over the area of the ellipse. This is the area of the ellipse, by the way, which we saw in the previous lecture, is the ratio of the time over the total period of the orbit, which we have expressions for as well through Kepler's third law. Right. So now, right, the goal then is to express AFvp as a function of area. And so, well, I guess we better get started on that. So AFvp, let's look at it. Well, here it is. It's pretty complicated, right? So we're going to reduce it to the difference between simpler parts, right? So specifically, we're going to notice that AFvp is the area of this slightly larger but simpler section. Right? Slightly larger but simpler section minus, right? So PVS minus this little triangle here. So I'll like just minus that little triangle there. So this little triangle here, PSF is that thing there, and PSV is, well, this like three-pointed weird thing here. Now the PSV is obviously not terribly easy to calculate, but we'll find out that it's not that hard. In fact, actually, we find that on this slide. So let's start with PSF though. So PSF is easy to calculate, right? Because it's a triangle. Triangles are pretty cool because we have a very nice formula for their area. APSF equals 1/2 base times height. Maybe you've heard of that before, right? Probably. So the remainder, of course, is to calculate what is the base and what is the height. So the base, of course, is SF, that line SF, and the height is PS. Okay, well, that's progress, but now, of course, what are these two lengths? So the goal, of course, is to express these in terms of E. Right? So, okay, let's look at these. Right? So what should we do first? PS. PS is a little bit easier. So PS. So PS, right, first of all, is QS, this longer length, times the ellipse scaling law. That's something we learned earlier, B over A times QS. So B over A times QS. So what is QS? Well, QS, of course, we have eccentric anomaly. We have this length, A, of this line here. QO is A. And so we can figure out what this opposite length is, right, just by using trigonometry. A sine E, right? A sine E, just, right? I'm not going to write down trigonometry. That seems like a little bit below us, a little pedantic. Anyway, so that's QS, and then we do the ellipse scaling law to get PS. Okay, good. So we can check that off. Score. SF is a little bit complicated because it's this length here, SF. Because, well, how do we calculate it? Well, first of all, we know that OF, that's OF, equals AE. That's the distance from the center of the ellipse to the focus. Maybe I should erase that. So that's OF. And then FS, or SF, is that length minus this little bit right here. Right? So this length minus this little bit right here. And so we can calculate what this little bit is, this QS, or sorry, OS, using the exact same relationship we saw before, except we now don't need the ellipse scaling rule. It's just the trig relationship. A, right here, maybe I should use my pointer, A cosine E, right? A cosine E. So A cosine E is OS. So this length SF, right, is AE minus OS, OF minus OS. And so OF minus OS, that's just that. And then we've got both parts of the area formula, SF and PS, and we could just do 1/2 base times height. Right. So we now have a nice expression for A PSF. So we have half of the terms that we need. It goes in there. And so now the question becomes, what is the expression for PSV? So let's just grab this term here so we don't forget it. Copy to the clipboard and go on to the next slide. Let's see, anything I didn't cover here? I think not. All right, so now I'll just paste that over here so we can use it again at some point in the future. There you go. Okay, so what are we interested in now? Remember, we got the expression for PSF, right? We have this triangle here. And now we're trying to find an expression for this section here, PSV. Right. All right, so how are we going to find that? So we're going to find that by using, again, the ellipse scaling rule. So specifically, we're going to actually, maybe I colored this wrong, we're actually going to calculate this area right here. Right. So we're going to find QSV, right? So that's the area all the way up to the inscribing circle right here. We want that area because it's easy to calculate, given that area, it's easy to calculate this area, which is QOV, and it's easy to calculate this area, QOS, right? So if we can calculate those two, we can find the difference between them, and that's going to give us QSV. Right? So QSV is a little bit easier to calculate. Of course, we're not interested in QSV. We're interested in PSV. However, we can notice that the area of this section up here, right? If we just integrate this section along x, right? Well, the integral of these, the integral is just the summation of these infinitesimal bars. And on the ellipse, the infinitesimal bars that we're integrating for PSV are scaled from the circle by a factor b over a. And so the integral along x for PSV is just the scaling ellipse constant times the area of QSV. Right? So we get this nice equivalence here. For PSV, in terms of something which is easier to calculate with Q, which is QSV. Let me just erase those little things here. Right, so QSV, let's find QSV. Let's get rid of that for a moment. Okay, so how are we going to do that? So basically for QSV, as I mentioned, we're going to take that section of the circle, right? First, let's take that section, let's get rid of all that. Take that section of the circle. Where's my green? No, I don't have green anymore. Make it green. Missed green here. Take that section of the circle. Well, what area is that, right? Well, that area is just, here we go, is just the fraction of the circle according to the by radians, right? So it's just 1/2 r squared e, where e is this angle in radians, right? Right. So I mean, yeah, this is a formula which hopefully everyone knows, but it's easy to see, right? Just because as e goes to 2 pi, then it becomes pi r squared, which is the area of a circle. So this is just the fraction of a circle that we're sweeping out here. So that one's easy to calculate. And of course, r is a here, so we get this bit. And that's in green, so I'll just box it in green there. So that's QOV, right, from here to here to here. So that's an easy one. And now we have QOS, right? So we want, in order to get this area, right, get that area, we need to take the green box and subtract off here I'll make it a blue box, right? This triangle right here. Right, and so again, triangles not too hard to define, right? The area of QOS is 1/2 base times height. The base here being OS, the height, which we already found earlier, and the height here being QS, which I believe we actually also found at some point. So let's just figure out what those are. 1/2 OS. Right, OS here is just A cosine E, right, cosine. And that's bit, cosine E. And of course the height is A sine E. Right, that's that bit right there, QS. Right. So we can find that expression for the QOS here, right? Did I call it anything? I'll call it blue, I guess. Right. And then we have QSV is the difference between those two. So we'll simplify a little bit and get our, this term is 1/2 A squared cosine, sorry, A squared, not AS. A squared cosine E sine E. Okay. Important to point out now that E is in radians, right? Because of course this formula here for the section of a circle, this formula doesn't work except unless E is in radians. And if there's a most common mistake in calculating these numbers, it's taking E to be degrees, right? When I see errors where we have a really large number of radians, it's almost always because someone used degrees on their calculator instead of radians. So make sure you remember that E is always in radians for these formulae. Right. So anyway, coming back, right, PSV we now have an expression for by, right, multiplying this whole thing here by B over A. Right. So now let's come back to our expression for AFVP, which is the area swept out. Right, which we have an expression for. We know what this is as a function of time. And now we're able to figure out what this is as a function of eccentric anomaly. Right, by plugging in this formula here and this formula, which I cut and paste from the previous slide, over there. Right, so this formula first, right, we have 1/2 let's see, here we go. Yeah, a 1/2 A B times A, because this A cancels that squared, and so 1/2 B over A times, or A times B times E minus 1/2 cosine E sine E. So that's comes down there. And then PSV from the previous slide, right, redirect there. Well, what do we have here? We can simplify that. Again, we have the B over A term here, right? So that that cancels out an A squared. And so we've got here our sine E, right? There's an A cancels out, just B over A. Sine E, right, comes out here, right? And then E minus cosine E shows up right there. Right. And so we have 1/2 AB, this stuff, minus 1/2 AB, this stuff. Now, fortunately, we've got this nice cancellation which occurs here. Cosine E sine E and cosine E sine E cancel each other out, so we can just cross off those two terms. And what we're left, well, I guess we cross off the cosine E part anyway. And what we're left with is 1/2 AB E comes straight down, and then the 1/2 AB is common, minus E times sine E. Right? AFVP, which we have equals AFVP, which we have an expression for, presumably as a function of time. And so this allows us to, right, have a formula which relates the eccentric anomaly to A as a function of time. Yep. So now let's go in and plug this into our expression for time for AFVP, right? So remember we decided to use this formulation of the problem because basically we want things to cancel out. We want this pi AB term on the bottom. And so we plug in for, I should use my cut and paste powers here. Right. Cut and paste. Right. So now we plug in our expression for AFVP in there. And now you see why we like dividing by pi AB, because now the AB's on the denominator cancel. And so we're just left with this 2 pi on the bottom. And so we have an expression now for a relationship between time on the one hand and eccentric anomaly on the other. And so this allows us, of course, to go one direction. It allows us to calculate T as a function of E, but it actually, at this point, it doesn't let us go the other way. So, but before, let me come back to that in a second. Before I get there, let me plug in now the formula from Kepler's third law for the period. And to simplify this expression a little bit, get rid of the 2 pi on the bottom. So we plug that expression in there, and because, right, we have a 1 over t term here, this gets flipped. The 2 pi goes to the bottom, right? And the a cubed over mu gets inverted. Right? So now we have an expression relating E and T, and we can just cancel off these 2 pi's, and we get this nice clean expression for E as a function of T. So a relationship between E and T. So basically, given E, right, now we can definitely solve for TP. It's unclear, of course, how to invert this expression, right? Can we go from T to E? That, unfortunately, is a much harder problem because this is what's called a transcendental equation. It doesn't have an explicit inverse. Right? It's hard to, so we have T as a function of E, but we can't invert that to get E as an explicit expression of T. Right? So we have to, that's a problem. Now, no such analytic solution exists. And this was, of course, recognized when Newton came up with Kepler's equation, and actually prompted the development of algorithms, right? A recursive or iterative not a recursive algorithms are different. An iterative way of solving for E as a function of T. So Newton's method was developed to solve Kepler's equation and obtain a function, or a map actually, because an algorithm is a map from T to E of T. And we'll talk about Newton's method in part B of this lecture. However, we have one more additional step before we get there, right? So remember the additional step. We can go from maybe T to E and E from T, but of course we need one more step, which is to go from E to F, right? So if we're going to convert back and forth between T and F, we need to be able to convert between E and F. And so that's a geometric relationship, doesn't require an algorithm, and so we'll discuss that on the next slide. Before we give that relationship, we're going to go through one more intermediate step, right? We want to get from F to E, which is the mean anomaly. So the previous expression described a relation from E to T. Unfortunately, solving this equation, right, this one right here, is a little bit dicey because, right, of the relationship between, the scalings on these numbers, right, is a little bit dicey because TP is tends to be very large and E tends to be very small, and so we actually try and introduce a intermediate variable, which is an angle, to get sort of this little bit better conditioned. And so specifically, we take an intermediate step to what's called mean anomaly, and then the conversion from mean anomaly to eccentric anomaly is through Kepler's equation. Mean anomaly is just a way of representing time as an angle. It's not time swept up, it's just conversion of time to radians, if you will. So it's basically if you take time and you divide by the period, so it's basically a unit conversion. So if we think of the units as radians per revolution, right? Then we can do this conversion here, dividing by revolution and multiplying by 2 pi radians per revolution. Right? So to give us mean anomaly here. Right? So basically, it's that conversion factor, 2 pi radians per revolution. Right? And that has that conversion factor here has a specific name. It's called mean motion, to give it a fancy sounding name, although it's just converting time to radians. So I don't know what more you could say about mean motion. It has its own letter n, so this is typically used. I don't know if I can say much more about it than that. Oh, I can give its formula, right? There's the factor, mu over a cubed, square root of mu over a cubed. In any case, so this intermediate value, I won't spend a whole lot of time on it, although certainly it'll come back into our discussions quite often. Not in any substantive way, but just as the next step between t and m. Right? Easy to convert back and forth between those two. Anyway, so mean anomaly is defined by the mean motion times the time, right? So the units on this mean motion are, of course, radians per second. This is period in seconds, right? And so this gives us a way of converting between time issued in seconds and a pseudo variable radians, which is basically just defined as the left-hand side of Kepler's equation, right? So instead of having on the left-hand side square root of mu over a cubed times t, we've got mean motion, or mean anomaly, right? So anyway, as I said, right, you could skip that step and go straight, but our solvers that we come up for solving Kepler's equation work with mean anomaly because it works better. It converges quicker. Right. So we do that sort of scaling conversion first, mean anomaly. Right. Yep. And again, I will cover the solution, right, how to get from mean anomaly to eccentric anomaly in part B of this lecture. We're not doing it right now. And we just showed how to get from time to mean anomaly. And now, to complete the diagram, of course, we need conversions between eccentric anomaly and what we're actually interested in, the physical thing, which is true anomaly. Because we're trying to convert time to true anomaly and back and forth. And so we need this final set of conversions. Fortunately, this one's not too bad. I can do it all on one slide, right? So it's not so bad. And how are we going to do this? We're going to do it in a way which doesn't seem promising, honestly, when you first think about it. But it actually works out all right. And so the basic rule is we're going to take this little line right here, right? This length right here of this weird diagram that we have, and we're going to express it both in terms of both true anomaly. Change my color. Both true express that same length here in terms of true anomaly and in terms of eccentric anomaly. So we're going to do express the same length in terms of both, and so this is it in terms of eccentric anomaly, right? Actually, I should have color-coded this better. I'll do blue instead. Now it's not. So blue, and in terms of eccentric anomaly, or true anomaly. Right, so the first one is easy. We've like done this same length like 3 times already. So here we'll do it the last time. Actually, we'll just say it, right? I mean, in terms of eccentric anomaly, it's easy. It's just A cosine E, right? I mean, because it's that triangle, right? A cosine E, this length is A, so done, right? In terms of true anomaly, it's a little bit more complicated because, right, it's this length and we have these lengths, right? So we have to actually do a little 2-step process here. So basically, this length is OF plus, and this is a little bit counterintuitive, SF, right? So why plus SF? Because look at this angle, right? Actually, what you get from cosine F is actually in this direction, and then it will be negative for larger angles than 90 degrees. So actually, we should really redraw this this thing as here, right? Here's our point. There's a focus. There's a center, and then dropping down here. And this length is AE, and this length is R cosine F, which of course AR, right? Yeah, no, that's R cosine F. So that's length R, and right, there we go. So, right, it's normally pointing in this direction. Of course, when you get greater than 90 degrees, it has a negative sign, so that's why it's we have a plus there. Right. So 2 parts. Well, we've almost got a relationship between E and F here, except for the fact that we've got this R in here. So we're going to get rid of it because we can find an expression for R in terms of A and E and F using the polar equation. So R is a function of F2. So we have to plug in there for R. And so we get that cosine E, let's divide by the A's. The A's cancel out, and it drops that A. And we get cosine E equals this 1 minus E squared over 1 plus E cosine F. So there's 1 plus E cosine F. That goes down there. And there's the 1 minus E squared. That goes there. And there's our cosine F. Drops down there. So we now have an expression for eccentric anomaly, or in terms of true anomaly. Now, are we done? Right? Well, not quite, because of course we actually want to be able to solve. Well, I guess this would give an expression for eccentric anomaly in terms of true anomaly, so it would give you like this direction. But we also want to be able to solve for true anomaly in terms of eccentric anomaly. Fortunately, there's a simpler version of this equation. Specifically, if we use the half-angle formula, we can use this tangent of E over 2, get the expression in terms of tangent of E over 2, as this coefficient here, right, times the tangent of F over 2. So, okay, that's much easier to work with, because we can just, well, again, it goes from F to E, but it's very easy to get the opposite direction, right? We just divide by this coefficient, and we get a tangent F over 2 equals square root of 1 plus E over 1 minus E, tangent of E over 2. And so you could just take the inverse tangent to solve for F in terms of E. So this expression here gives us both directions, converting back and forth between E and F. Yeah, so there's the other expression. A quick side note, although I don't want to dwell on it because it's rarely used. There is a way of bypassing F entirely and putting the whole thing in terms of true eccentric anomaly. So remember, we got T to M to E to F, right? We can actually right to R, right, through the polar equation. We can actually skip F entirely and write the polar equation directly in forms of E, although we don't usually use that because it's like a little bit, I don't know. E is not a very important number, right? If you're going through E, you might as well go through F. But you can skip that step entirely if you're just looking for R, and because we have a version of the polar equation expressed directly in terms of E, as opposed to, of course, the equivalent, right, which is 1 plus E cosine F of t. So you could go directly from F to R instead of finding F, or go directly from E to R as opposed to finding F and then E to F and then F to R. Again, very few people use that equation, but it's there, and it's interesting, right? All right, finally, right, here's remember T, our progression here, T to M to E to F, and then possibly to R, and backwards and forwards. With the caveat that this direction requires Kepler's equation. This direction does not, right? We can solve for T in terms of E. Right? So there's actually a hard way and an easy way of this progression. So specifically, this direction is hard, and this direction is easy. Right? So in to conclude part A of this lecture, I'll just go through an example of the easy way, right? Because it's easy, right? And then part B of the lecture, we'll have to figure out how to solve Kepler's equation to do the hard way. Right, so the easy problem is, let's say, suppose we observe an orbit around the Earth. A is 10,000. Maybe we got that from our H and our E, found our geometric invariance. And we want to predict the times at which the distance to the Earth will be 14,147 kilometers. For some reason, I'm not sure why I chose that number. So this is the picture right here. Here's the Earth, right? And there's this line, maybe 14,000 kilometers here. And we want to find these 2 points, right? The times at which we hit that circle. Note that there's 2 points at which we're in this orbit, right? Orbits go increase and decrease. So there's an ascending time and a descending time, right? So time when we're heading out towards apogee and a time when we're coming back towards perigee. So there are going to be 2 solutions to this problem. Okay, so where do we get those 2 solutions? So let's follow our steps. Starting with R, we will then use the polar equation to find F. Right, so here's the polar equation. We got to invert the polar equation, of course. So this is P. We've substituted in. So of course we do that, right? We move multiply by the denominator, divide by R, and then move the 1 over to the right-hand side, and so on and so forth. And we find our expression for F in terms of R, right? And then we plug in our values for R and do an inverse cosine on F. Or just of all that. Now, of course, inverse cosine has a quadrant problem in that there are 2 solutions to an inverse cosine problem. And so we don't know which one we're at because we're not given any additional information, whether we're headed out or coming back. And so if we had the velocity vector, we could determine this, but we don't. So we just have to take both solutions. Right? Now, I've expressed this in degrees because they're nice round numbers, and I don't know, because people are familiar with degrees. But remember, when we go right to eccentric anomaly, we want to go into radians. So be aware that while I express F in terms of degrees and I express eccentric anomaly in terms of degrees, these should be in radians. So I just did it because why not? Anyway, so we got F at 2 values of F, and now we apply this formula to invert the do the inverse tangent of this to tan inverse, right, of this expression, and we get E. So inverse tangent, fortunately, doesn't have that same quadrant ambiguity, but we still have both values of F that we're testing here, 1 and 2, and so that yields 2 values of E as well. And so the two values of E here are plus or minus 146 degrees, or that's what my calculator tells me anyway. So there's a bit of a problem here with terms of ambiguity and angle, right? Because we went from 160 degrees and 200 degrees to plus or minus 146 degrees. So we went, so in particular, clearly plus 146 corresponds to 160, but negative 146, does that correspond to 200? Well, not really, because it's the wrong revolution, right? It was like you've added a period to it. Unfortunately, this quadrant ambiguity and the 2 pi ambiguity or the 360 ambiguity shows up quite often. And so actually, when I go to the next step, I would actually like to resolve that ambiguity. So keep that in mind. So let's plug this into first convert to radians. And then actually I would like to convert that negative 146 degrees. I would like to add 360 to it. So that obviously, right, it makes more sense. We don't like dealing with negative angles. We assume this is on the same rotation, right? So right, I mean, there's a ambiguity in this angle here, right? Is this negative 146, or is it positive 216, 214? We've chosen to positive 214, convert it into radians, and then we plug it into Kepler's equation here, and we just plug in, right, everything's straightforward. We get our value of mean anomaly as 2.67 radians and 4 radians. Right? So again, we've not chosen to use that angle, we've chosen to use this angle. So that's mean anomaly. Of course, mean anomaly doesn't mean anything. We've got to then, it's just a placeholder for time. And so now we've got to solve for time, m equals nt. Mean motion here, right, is just that conversion factor, radians per second here. And so we solve for time as m over n. And we, yeah, there it is. And we get two values for time, 3,600 seconds and 6,400 seconds approximately. So we've now determined the two times in the orbit, future times, because we decided not to go into the past, into the history. So we're thinking future times. Of course, technically, there's infinite number of times which this is going to happen. You could just add multiples of the period to both of these numbers. But that's just pedantic. So let's not do that. Anyway, so, right. So now we've solved, right, 1/2 of the problem at least, going from R to T, right, through that intermediate step where we had mean anomaly and eccentric anomaly. And now in the next part of the lecture, when we come back, we're going to talk about going this direction, specifically converting from mean anomaly to eccentric anomaly. So we will come back to that problem when we return, but now we'll take a break.